In this video, we're given the curve y equals 25 minus x squared, and what we're going to be doing is inscribing a rectangle whose corners hit our curve. And we want to maximize the area, perimeter, and then the sum of the area and perimeter of that rectangle. So we know that this point here is going to be 5, 0. This point here is going to be negative 5, 0. This point here is going to be 0, 25. So that tells us that x is going to be in between 0 and 5, and y is going to be in between 0 and 25. Now you might be wondering why x is between 0 and 5 and not negative 5 and 5. I'm deciding to let x just be this part right here, only half of the width, because it matches up with our Cartesian plane. And there's going to be my y. So I'm basically measuring x and y like we would on a normal graph in rectangular coordinates. So first thing, the area then of this rectangle we're going to maximize. This is x plus another x, so the width is 2x times the height, which is y. We have two variables there, but we have a constraint between x and y. So we're doing constrained optimization, so 2x minus 25 times 25 minus x squared equals 50x minus 2x cubed. Alright, so now we're going to do the derivative and see what we got. So a prime equals 50 minus 6x squared. Set that equal to 0, and you're going to get that x is the square root of 25 over 3, or 5 over rad 3. I'm not too worried about rationalizing the denominator. Now if we wanted to do a number line analysis on this, 5 over rad 3, well, remember you check your numbers in A prime. Anything smaller, say 1, 50 minus 6 is going to be positive. So that tells me the area is increasing up to 5 rad 3, which we know is 0. Anything bigger, say 4, 6 times 16 is going to be 96. 50 minus 96, clearly negative, decreasing. So this is a relative max. Now our minimum area is going to come at x equals 0 or x equals 5, because if x is 5, y is 0. If x is 0, y is 25. We don't have a rectangle, we just have a line. So this is going to be our max. This is going to give us our maximum area is x equals 5 over rad 3. Now to get our y, we plug it in. We have 25 minus 5 over rad 3 squared, which if you do the work on that is 50 thirds. So there's the dimensions that yield the maximum area. If you want to actually multiply that out, you're going to get 500 over 3 rad 3 is our maximum area for this situation. Let's go ahead and move on to perimeter. Now the perimeter, based on the way we have this written, we have an x plus a y plus an x plus an x plus a y. So 4x plus 2y. Or, now again we're going to use our constraint, so 4x plus 2 times 25 minus x squared. If I simplify this, I'm going to get 4x plus 50 minus 2x squared. Okay, and we might go ahead and write that as a regular quadratic. Not necessary for where we're heading, because we're going to take our derivative. We already know what the minimum will be. The minimum is going to happen when x is 0 or 5. So we take our derivative, we get 4 minus 4x. This one's an easy one. If we set that equal to 0, then when that gives us x equals 1 as our critical point. If x is 1, y is 24, excuse me, and that's when we'll have our maximum perimeter of 4 plus 48, or 52. So perimeter is really not too bad on this one. Okay, lastly, they wanted us to maximize the area plus the perimeter. Well, we already found the functions in terms of x, so let's just add those together. For area, it was 50x minus 2x cubed. And then for perimeter, so plus 4x plus 50 minus 2x squared. Okay, so this answer might not work out as nice as the other two did. So we're going to combine like terms, simplify as much as we can. There's not a whole lot we can do. It's minus 2x cubed minus 2x squared plus 54x plus 50. Again, this sum will be 0 when x is 5 or 0. So we're looking for some point in between there that's going to maximize it. So taking a plus p prime, we'll call it, is going to give us minus 6x squared minus 4x plus 54. We're going to set that to 0, and probably the easiest thing to do is go ahead and just use the quadratic formula. Now if you do that, you get two answers. One is negative 3.3518 approximately, and the other one is approximately 2.6851. Now only one of these fits within our interval, so let's not worry about that one. So there's the x that's going to yield the maximum sum of area and perimeter, and the corresponding y, well remember y is 25 minus x squared, that's our constraint, which as a decimal is approximately, well I'll just go to 2 decimals on this one, 17.79. So those are the dimensions of the rectangle that would give the largest sum of area plus perimeter.